Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming at you from the Mozaic Works studios. And what I have for you today is a deeper dive into cell architectures. The idea of cell architectures has recently been discussed more and more because of one case study from Slack and because AWS is pushing it. So I want to go a little bit through the details and explain what is cell architecture, show you that it's not a new idea, it's actually more than 10 years old, and then discuss a little bit what Slack has done, and finally talk about the trade-offs of this architecture, because one thing you need to always keep in mind, whatever type of architecture you choose, there will be trade-offs. There's no architecture that has only benefits. That thing doesn't exist. So when you read marketing documents, when you watch talks about a specific architecture, pay attention to this, because often what they do is they discuss about a specific problem and how this specific architecture fixes that particular problem. And then they go into sale mode and tell you, look, AWS has this thing and those things that help with cell architecture. So it seems like it's very easy to implement. And finally, they talk a little bit about the challenges, but usually it's just a few minutes, just a very little discussion about that. And if you want to be more aware of what architecture best fits your environment, then you need to pay attention to the trade-offs and start thinking about what are the things that could go wrong and what are we losing when we are gaining the benefits. The benefits are real, but what are we also losing? What are we trading those off on? So let's start by looking at an older article, which is 9 May 2012, Cell Architectures. This was published on highscalability.com. And it describes, as you can see, it's 9 May 2012, we are in 2025, so it's 13 years old. This was probably older because usually by the time articles are published, these things exist in practice, so it's obviously an older architecture. So we could say it's probably around 15 years old. And let's see, a consequence of service-oriented architecture is the burning need to provide services at scale. The architecture that has evolved to satisfy these requirements is a little-known technique called the cell architecture. Cell architecture is based on the idea that massive scale requires parallelization, and parallelization requires components be isolated from each other. These islands of isolations are called cells. A cell is a self-contained installation that can satisfy all the operations for a shard. A shard is a subset of a much larger dataset, typically a range of users, for example. So fundamentally what this is encapsulated sharding. That's how I think about it. So sharding means we take a large database, a large dataset, and what we are doing is splitting it into pieces based on specific criteria. So one example would be if you're dealing with people, if their names start from A to D, they are in the first shard. If their name starts from D to G, they are in another shard, and so on. Not the best way to do that, obviously, but it's just an example. Another example could be based on location. So, and this is what I believe Slack did. It's likely that that's what they did. If your product is meant to go globally, then it makes sense to have separate shards for people from separate locations. So you might have a shard for Western Europe, Eastern Europe, Middle East, East US, and so on, right? And conveniently, if you think about AWS, this kind of match the availability zones in AWS. So you could use sharding to split your data sets between the different availability zones. But then you have a problem because you want the behavior to be in the same place with the data. If you have the behavior in the same place with the data, this leads to encapsulation, is better modularity. It can scale up and down independently based on what the needs are. And very importantly, on larger installations, you are not paying for traffic between availability zones, which can be an issue. So because of this, what you have in cells is basically an encapsulation. You have a shard for a data set plus the behavior for the data set, right? All right. So that makes sense. Cell architectures have several advantages. Cells provide the unit of parallelization that can be adjusted to any size as the user base grows. Right, so you can scale up and down this based on your particular cell. Cells are added in an incremental fashion as more capacity is required. Yeah, maybe, we'll discuss. Cells isolate failures. One cell failure does not impact other cells. This is very important. This is one of the big advantages of cells. You can have one cell completely failing. This doesn't affect the rest of the world. It just affects those people from that particular zone or from that particular shard. Cells provide isolation as the storage and application horsepower to process requests is independent of other cells. Yeah. And particularly with cloud infrastructures where you can scale up and down or have them completely separated. Quite nice. Cells enable nice capabilities like the ability to test upgrades, implement rolling upgrades, and test different versions of software. Yeah, so you can make experiments into one cell. You affect only that one and you don't affect the other ones, which means that you can try, for example, upgrading your engines to the latest version on one of these cells, see if it works correctly. If it doesn't, you roll back, but you also know not to do it on the other cells until things get fixed. Cells can fail, be upgraded, and distributed across data centers independent of other cells. Yeah, so you can also have multiple cells per database in a way, if you really need to, although it's not the best idea. Ideally, you'd keep things as simple as possible. It's already quite complicated in terms of operational monitoring, all this stuff, because these are some of the things that you're trading off for this simplicity. But you are simplifying a little bit the deployment, well, not the deployment, the development, experimentation, recovery. No, you have a few advantages there. A number of startups make use of cell architectures. Tumblr, Flickr, Facebook, and Salesforce. The key to the cell is you are creating a scalable and robust MTBF, so mean time between failures, friendly service. Mean time between failures is a very important indicator in reliability and resilience. So basically what it means is on average how long it takes you, now on average how long until the next failure. Because remember, so if you are mostly used with programming and not so used with architecture, this might come as a shock, but things fail all the time. So the thinking is resilience is that your product will stop working at some point. You don't know exactly when. And we are measuring this mean time between failure to have an idea of kind of when this will happen and try to make it, you know, as few failures as we can, which means higher mean time between failures is better. But you will have failures. That's a given. It's not something maybe or presumably or if. No, things will go wrong because particularly as your complexity of your architecture complexity increases, things are bound to go wrong. Hard drives fail, CPUs get sensitive to moon phases or, well, mostly sun magnetic fields, and so on. So there can be fires, there can be natural disasters, flooding, hardware fails. There are a lot of things that can go wrong. The network can go down for a number of different reasons. The OS may start behaving in weird ways. So things will go wrong. That's a given. The only thing you can do is to make sure that those failures are as rare as possible and affect as few people as possible. And one nice thing about cells is that there's a higher probability that a single cell will fail than the whole system would fail, right? So the mean time between failures in this case will tend to be higher, or at least not affect as many people. So this was the initial article, and let's see a little bit how these companies were using. So Tumblr, users are mapped into cells and many cells exist per data center. Each cell has an edge-based cluster, service cluster, and Redis caching cluster. Users are home to a cell, and all cells consume all posts via Firehose updates. Background tasks consume from the Firehose to populate tables and process requests. Each cell stores a single copy of all posts. So Tumblr would be similar with Reddit, I think. I'm not sure. Are you still using Tumblr? Because I haven't heard about Tumblr in a very long time. Flickr uses a federated approach where all user data is stored on a shard, which is a cluster of different services. Facebook, the messages service has as the basic building block of their system a cluster of machines and services called a cell. A cell consists of zookeeper controllers, an application server cluster, and a metadata store. And Salesforce is architected in terms of pods. Pods are self-contained sets of functionality consisting of 50 nodes, Oracle REC servers, and Java application servers. Each pod supports many thousands of customers. If a pod fails, only the user on that pod are impacted. Great. So this is where we were in 2012. Where are we now? I found this article, which is from 2023. I also watched the video that I will post in the description, and you can watch it for yourself. It's a talk from the AWS conference where a Slack engineer describes what they did and why and so on. But this is a good start. So in recent years, cellular architecture has become increasingly popular for large online services as a way to increase redundancy and limit the blast radius of site failures. Right. So one thing you can also do is to create redundancies, which means you could have multiple cells for the same shard and replicate the shard somehow, although you see how that can become quite difficult if you go that way. Another thing is you could have the shards, instead of being completely separated, just have them overlap a little bit, so that maybe you have some extra cells, but each user is covered by 2 cells, let's say, and then in that case you have redundancy. Now all of these have their own associated complications, so we have to be aware of that. In pursuit of these goals, we have migrated the most critical user-facing services at Slack from a monolithic to a cell-based architecture over the last 1.5 years. So it hasn't been easy, right? We've done this for quite some time. In this series of blog posts, we'll discuss our reason for embarking on this massive migration, illustrate the design of our cellular topology along with the engineering trade-offs we made along the way, and talk about our strategies for successfully shipping deep changes across many connected services. So background, the incident, at Slack we conduct an incident review after each notable service outage. Below is an expert from our internal report summarizing one such incident and our findings. At 11:45 a.m. PDT on 30 June 2021, our cloud provider experienced a network disruption in one of several availability zones in our US East Coast region, where the majority of Slack is hosted. A network link that connects one availability zone with several other availability zones containing Slack servers experienced intermittent faults, causing slowness and degrading connections between Slack servers and degrading service for Slack customers. At 12:33, so this was 48 minutes later, the network link was automatically removed from service by our cloud providers, restoring full service to Slack customers. After a series of automatic checks by our cloud provider, the network link enters service again. At 5:22, so about 5 hours later, the same network link experienced the same intermittent fault. At 5:31, the cloud provider permanently removed the network link from service, restoring full service to our customers. At first glance, this appears to be pretty unremarkable. A piece of physical hardware upon which we have relied failed, so we served some errors until it was removed from service. However, as we went through the reflective process of incident review, we are led to wonder why, in fact, this outage was visible to our users at all. Slack operates a global multi-regional edge network, but most of our core computational infrastructure resides in multiple availability zones within a single region, US East 1. Okay, I'm gonna skip this. This enables builders of services to architect services in such a way that the availability of the entire service in a region is greater than the availability of any one underlying availability zones. So why didn't this strategy work out for us? Why did one failed availability zone result in user visible errors? As it turns out, detecting failure in distributed systems is a hard problem. A single Slack API request from a user may fan out into hundreds of remote procedure calls to service backends, each of which must complete to return a correct response to the user. Our service frontends are continuously attempting to detect and exclude failed backends, but we've got to record some failures before we can exclude the failed server. Alright, we might class the outage above as a gray failure. In a gray failure, different components have different views of the availability of the system. In our incident, systems within the impacted availability zone saw complete availability of backends within their availability zones, but backends outside the availability zones were unavailable, and so on. So this is an issue when it's not very clear what has failed, right? And the system is kind of not knowing what to do, more or less. I'm oversimplifying, but that's kind of what it is, and it's difficult to understand what has happened. Okay, our solution. Availability zones are cells, and cells may be drained. Like a lot of satisfying infrastructure work, an easy drain button is conceptually simple yet complicated in practice. The design goals we chose are: remove as much traffic as possible from an AZ within 5 minutes. Drains must not result in user visible error. So draining would mean we kind of move to another cell, right? Okay, drains and undrains must be incremental. When undraining, an operator should be able to assign as little as 1% of traffic to an availability zone to test whether it has truly recovered. The draining mechanism must not rely on resources in the AZ being drained. The main strategy we settled on is called siloing. Services may be set to be siloed only if they only receive traffic from within their AZ and only send traffic upstreams to servers in their AZ. The overall architecture effect of this is that each server appears to be n virtual services, one per AZ. Importantly, we may effectively remove traffic from all silo services in an AZ simply by redirecting user requests away from that AZ. If no new requests from users are arriving in a siloed AZ, internal service in that AZ will naturally quiet and they have no new work to do. So they basically split into cells based on availability zones. And that was the siloing approach. And now let's look, this is a longer series of posts, but instead of me going and reading through those, let's just look at what has kind of promoted this more or less, which is AWS. AWS has a guidance for cell-based architecture on AWS, and you can see here they have a diagram. And what they are saying is that you split into cells, and then you have this container service. You have a routing layer. This is the important part. So you have a routing layer that will know how to route for a specific user, right? Because you need somehow to know where to go. Now it can be based on location, as we said. It depends on the key you use for your cells, for your shards first, and then for your cells. Routing information, user to set cell mapping is stored in Amazon DynamoDB. There is a fixed number of independent clusters that store copies of the data. For new user, the cell router pushes the new user information to all clusters. So it's again trying to have a more encapsulated approach where each cell kind of decides, okay, do I take this new user or not? And some responsibilities pushed there instead of having a central coordination thing. And yeah, it's probably a good idea to have this duplicated, because if you manage to have a user data in multiple places, at least two, then there are fewer reasons for failure, which means higher mean time between failures. The architecture is divided into a large number of independent cells of fixed size. The cells contain all application logic and storage. Yeah. Each cell has monitoring and alerting capabilities. There is also a central dashboard which contains aggregated information such as number of cells with and without errors. Cell creation and update is automated. Updates are first deployed to a canary cell. That's a good one. You deploy to a single cell, whatever let's say you make some changes to your software, push it, but to a single cell, verify that it works, and then continue upgrading the others. Changes are streamed from all cells to a central data lake where they can be queried using SQL. A rebalancer can move users between cells and also create new cells as needed. And this is very important. It doesn't sound very important, but it is, because rebalancing is an important part of sharding. Okay, so now let's talk a little bit about the trade-offs, because as usual in these documents, you see the benefits. Now let's talk about some of the downsides of this. First of all, let's be clear, there are there are some good contexts in which to make this, and Slack was in a perfect context for this. Slack's users are spread around the world, and they communicate within specific groups, which means that you can kind of group them based on that. So you have a natural way of doing sharding. It can be based on the uh, Slack groups they are in, right? And then it can be also geographical and so on. But the thing is, you can actually do this. It's a very natural approach. This kind of approach doesn't apply to all businesses. I mean, if you try to shard users, uh, first of all, it needs to be a large enough business. It's if you're just doing a startup right now, you have few users. I don't think there's any reason to start with sharding, because why do that? It's additional complexity. And this key selection is critical. This ability to select how you split is actually very, very important. If that criteria is very clear and it makes sense for the business, that's great, right? But if you make it artificial, then things become much more complicated, because remember, you need to make automated decisions about where to place a specific user in which shard. And that needs to be based on some criteria. And then the very important thing, let's assume you have a lot of success and your databases are increasing. Chances are that one shard will increase faster than other shards. Maybe you have more success in a specific location, or maybe you have more success within, specific groups that become more popular, or and so on. So it's very important to understand that, because at some point you'll need to reorganize your shards. That's what they are talking about, rebalancer. And that rebalancer needs to do it, well, ideally automatically, because if you need to go through thousands of users or tens of thousands or hundreds of thousands and decide manually where to put them, not that great, right? So you need some criteria to move this, to rebalance users. Now, how would you do that if you haven't had the criteria correct the first time? Well, you'll need to move some data from here to there, and that's extra work. If you need to add more criteria, that can become costly in terms of implementation, in terms of testing, but also in terms of data transfers, particularly if you're using cloud providers and you need to move data between availability zones. And that can be costly. Well, depending on how large your data store is. So rebalancing is complex, and having a natural key for sharding is very, very useful. Let's talk about other things. So operations. How do you run this? Well, you need a lot of monitoring. They mention here monitoring. Monitoring is not an easy task here, because you need to gather a lot of data from each cells, and you need to get alerts, and you need to be very careful what to do with those. Some of the alerts will need to be acted upon automatically, because one thing you want to do is to be able to take down a cell, like they were describing in Slack, and maybe move some of the activity to another one that replicates the same or similar. So it's either the same cell twice or parts of the shards are twice in other cells. So monitoring and responding to these alerts might be quite complicated. And it's, you see, these are things that you need to play around with, because they are pretty difficult to get right. You need to have some specific goals and start from that. You could have bottlenecks on specific shards, because if one of the shards is increasing, then that cell might not work as well. And yeah, if things are very separate with the cells, if you can scale up and down each cell, then there's no problem. If you can duplicate the cell, even better, although that might be a bit complicated. Other things, so yeah, you have complexity in deployment, you have complexity in operations. But I think the other thing that you need to pay attention to is if you ever need to do transactions between shards, in this case between cells, you get into the world of distributed transactions, which are not very fun to do, and they can lead to a lot of different issues. You need to be aware of the cap theorem in that case. So yeah, you probably, if you need, one nice thing about splitting things, data plus the behavior, having it completely separate, it's nice because you can work on each one of these cells separately, but it's possible if everything is separate. So if you need to update multiple cells with a transaction behavior, you'll start getting into some complexity. It's best if you can avoid this, but yeah, it's not always possible. And now finally, the last thing I'd like to talk about is compare this approach with microservices, which is the other style of architecture that's very prevalent nowadays. So microservices, what they do kind of the same thing, only at a smaller scale. And instead of having the data split into shards, with microservices, we split the domain model into subdomains and bounded contexts, and then have microservices within a bounded context, which is a more complex way of saying that microservices are more granular and they operate on parts of data without necessarily providing the same, and actually without providing the same behavior. You still have encapsulation, you still have modularity, because each microservice is encapsulated with the data store, and you have this type of encapsulation, and then microservices need to communicate between them. But overall, microservices are more complex than cell architecture, because cell architectures is basically, if you have a natural criteria for sharding, you say we use this criteria for sharding, we will replicate all our behavior on multiple servers working on that specific data. We'll have a routing on top, and that's it. Simplified. Microservices is all that, plus we need to identify granular behavior that fits with granular data. And it offers, with more granularity, you have the ability of recomposing the behavior. And this is one advantage that you'll find with microservices. If, let's say, you already have a type of behavior, but then you come and say, we want to implement another business case. Well, we already have these things in place, so we can reuse the microservices that we have and just add new things on top. Usually, this should be possible if you're doing things at the right level of granularity. With cells, you'll need to modify the cell, and then it depends on how modular you are inside the cell and not between cells. So also another thing with microservices is that they are best fit or better fit for situations when the scaling up and down is granular and it's not based on a clear criteria. Scaling cells up and down is possible, but if you can shard based on criterias, as we discussed. But with microservices, if you split in smaller things, it might happen that sometimes this side of these 10 microservices are more used and they scale up. The other time, these 20 microservices need to scale up and down and so on. So there are advantages and disadvantages to all that. Another thing that I'm noticing is that I think it might be quite difficult to switch from sharding to microservices or from microservices to sharding. Depending on how many microservices you have, on how complex the application is, this switch is quite time consuming and costly in terms of implementation and everything that it entails, operations, automation, all of that. But the good thing, if you start from a monolith and then you split it based on what fits your context, then you can go either way. It's probably easier to switch to cells than it is to go all the way to microservices, unless you've done a proper domain model analysis in the beginning or while developing, while architecting. Right, so these are my thoughts about this. But one general thing that I like you to remember is when you see stories like company X chose architecture style Y because it solves all the problems, that's great for them, but it doesn't mean that this thing actually works for us. Architecture is about making decisions that are relevant within your context. And you have to take your context into account. It's a socio-technical system. It's not only about the technology. Right. So sometimes the technical aspects push us, but most likely it's about the business. It's about the domain. What do we want in terms of the business? What do we expect? What issues do we face? Okay. And that's where you need to start. So whenever you see things like company X using technology Y or architecture Y and the large tech providers pushing this, that's perfectly fine, but understand what are the trade-offs and pay a lot of attention to the things that they just skim over. Those are the most important parts when making an architectural decision. All right, that's it from me this time. And I want to encourage you once again to write comments, ask us questions. I had some people reach out to me on LinkedIn and asking me for connections. That's great. I'd be happy to get connected with you as well on LinkedIn. And if you have any suggestions, any questions, any follow-up, any things that you didn't understand, anything that you'd like to learn about software architecture, software design, programming, I'm now looking and experimenting more and more with uh, AI assistants for programming, and it's quite interesting to see what's possible right now. So if you are interested in any of these things, let us know. Let me know in the comments. Thank you kindly for the view, and until next time, remember to think, design, and work smart. See you next Saturday.